We present a new approach for real-time Kelvinlet-based image deformation and video time warping. There are numerous applications to image deformation and video time warping. From photo editing to video compositing, these solutions are very relevant to the creative industry. Our contributions are the extension of the Kelvinlet deformation field to inverse warping. They use elastic properties to preserve smoothness and volume. A real-time warping algorithm for both images and videos, which has intuitive mathematical basis and implementation, and also has a simple per-pixel parallel GPU implementation. The results can also be easily anti-alias and mitigate artifact generations. Our paper also discusses issues as temporal aliasing on digital videos. Based on the work of D. Goes and James, the regularized Kelvinlet brushes are a set of elastostatic deformation methods, which means they tend to preserve the volume of the object. We'll be using only a share of their work, which is the basic brush they provide equations to in their paper. The Kelvinlet equations take into account two main variables: the Poisson ratio, which increases proportionally to the elastic properties of the desired simulated object, and the brush size, which intuitively is the size of the deformation influence. We can see these properties on the video to the right. We demonstrate on the right the set of variables that define the deformation process. We select the point P0 and drag it to the point P, and thus for every other point P in the pixel domain, we calculate its respective movement. Here we list some of the mathematical expressions that involve the two parameters and their properties. Here, for a point P, we compute the deformation Kp as a proposed displacement to the point given. Here we have a forward deformation example, where we take the point P and transform it into a point Q in the output space. We do that by computing T, which is the sum between the point P and the dislocation Kp. The inverse transformation occurs when we calculate for a point Q in the output space, a point P in the input space that will map to it if transformed by T. We represent this by the following arrow containing T to the minus 1. The reason we do this is because, well, it does not require us to fill the possible gaps between the pixels in the forward math output. This leads to faster computation and much higher quality of the output. We have a problem, however. The function Kp is nonlinear, meaning that its inverse does not have a trivial solution, which is why we need the Gauss-Newton method. The Gauss-Newton method, as many of you may recall, is a linear approximation method. Given the transformation T, we set the method's objective to find the point P that minimizes the difference between its transformation and the given point Q in the output space. In order to do that, we iterate over improved solutions pk of the first order Taylor expansion, which gives us the following expressions. For that, we need to compute the Jacobian matrix for the transformation at the points pk. The equations to do so are in the supplementary material. We can, through calculus, retrieve the closed form equation for the iterations. We execute the following algorithm to approximate the inverse for a given point Q. First, we set an initial guess of the inverse point to Q. While we haven't reached the stopping condition, which measures the approximation error with an upper bound of 50 iterations, we solve the Gauss-Newton linear system for the current iteration. Know how the approximation starts at Q and strives to find the optimal pk that is mapped by the transformation T to the output point Q within sub-pixel precision. On the right, we show the number of iterations required for each pixel of the Mandrell's picture deformation. We see by the histogram that most pixels didn't even surpass 15 iterations before reaching the break condition. Finally, it is worth mentioning that this algorithm can be executed independently and in parallel for all pixels Q in the output image space. The algorithm we just showed is the same for both images and videos. In this presentation, we are showing examples in image deformation solely because it's easier to visualize. The only difference is that video time warp uses a three-dimensional space since it considers the video as a volume, and this is a common approach used in previous work. We should discuss important details as discussed in the paper. The transformations can dislocate and break boundaries. For that, we propose a fixed boundary extension of the Kelvinlet force field. There is also aliasing, and we show how to use the deformations gradient for anti-aliasing. There is also the possibility that the transformation is non-invertible, and we show in the paper how to detect and handle non-invertible fields. As we deform both the 2D space and the 3D space, it is natural that edge pixels of the image or video are deformed as well. This, unfortunately, leads to undesired border artifacts, such as the one around the grid shown here. To mitigate this, we use a controller function on the deformation. This is nothing more than a higher level method which takes in the position of the point and decides whether it should move fully or only a fraction of the proposed displacement. To do this, we establish an influence radius sigma that defines what distance up to the borders of the space should the deformation influence decrease in a curved rate. We need to update both the deformation and the Jacobian matrix of the deformation if we use this method. We can see on the right a video demonstrating the radius influenced by colors and how it slows down the deformation on the grid by its side. Pixel displacement can lead to aliasing, much like in this example. We can use an isotropic filtering by using a mip-map pyramid. This is easily implementable and natively supported by OpenGL. To do that, we consider the following equation which describes the local expansion or contraction at each pixel through the Jacobian matrix. From this, we can derive a mip-map level for a given pixel. And once we do this, we have a clean anti-alias result. But what would happen if the contraction equation was less than 0? We would have a non-invertible deformation field. And for that, please see our paper for more information on this. Well, for the implementation, we had a CPU implementation in Julia for image deformation, and we achieved an efficiency of 0.042 seconds on a 512 by 512 image. We also used Julia for implementing a MIP map for video time warping. We also did a GPU implementation in C++ and OpenGL, mostly for high efficiency video time warp. And to do that, we used a Gauss-Newton inversion, but calculated in the fragment shader. We achieved an efficiency of 300 frames per second in a Full HD 1080p video. Here, we see the results of Krita's image editing software deformation compared to ours. Different from our result, Krita's result does not preserve the volume and result in edge discontinuities and aliasing. Much like the previous comparison, our result is smoother and generates no artifacts. Here we show how the inverse deformation has more precision when computing the output pixels. We can prove so by showing the results on a fractal image. Our result trumps the forward map Kelvinlet deformation as it generates clean and precise results, while the other produces blurred fragments generated from the post deformation interpolation. Here we exemplify a simple transition the video time warp can generate. The input is an instantaneous transition of colors, and the output is a smooth circular transition. In this example, our goal is to slow down the zoom out movement centered on the flower. We do so and result in the video to the right, where the flower only zooms out smoothly around the end. In this other example, our goal was to stop the water from filling the center of the cup for a longer time. In the result, we see that the cup is filled to the top before filling the center. An issue that arises when considering blending flames throughout time is temporal aliasing. Our perception of the video to the left may be continuous, but that does not mean that it is continuous through time. As seen in the right, we can see that in the column time slice, there are rough edges between frames, which can lead to undesired deformation results. These results are exemplified here, where in the right, we see that a small deformation generates discontinuities inside a specific frame. We can try to mitigate this the same way we mitigate aliasing in 2D images. However, the results get blurred really easily. This can be well mitigated, however, by having slower or high frame rate videos, which thrive on frame continuity. In conclusion, we presented an extension of the Kelvinlet deformation field to inverse warping. We also presented a real-time warping algorithm for both images and videos with a simple per-pixel parallel GPU implementation that generates smoothly high-quality deformations. We propose a fixed boundary extension of the Kelvinlet field, and we also show how to use the deformations gradient for anti-aliasing. We show how to detect and handle non-invertible fields on our paper. Our paper also discusses issues such as temporal aliasing on digital videos. We would like to thank our sponsors and everyone that helped us with this work. Thank you very much for your attention.